Hello, students. In today's lecture, we are going to learn about systems of particles and rotational motion. NCRT section 6.12 and 6.12.1. This is disclaimer. Learning objective. By the end of this lecture, you will able to understand the concept of angular momentum for fixed axis rotation, relationship between components of angular momentum and torque, and conservation of angular momentum for rotation about a fixed axis. All right. So in today's lecture, we will cover 6.12 angular momentum in case of rotation about a fixed axis. After that, 6.12.1 conservation of angular momentum. All right. So 6.12 angular momentum in case of rotation about a fixed axis. So before starting the angular momentum, so recall what momentum means in linear motion. So in linear motion, it tells us how much motion a body has and how difficult it is to stop or change that motion. That is called linear momentum, and it is given by L is equal to mass into velocity. Now, when a body is rotating, when a body is rotating, we need a similar concept to describe how much rotational motion the body has. All right. So that quantity is called angular momentum. So angular momentum is the rotational equivalent of linear momentum. It tells us how much rotation the body has and how hard it is to stop or change that motion. All right. If we talk about an example, so just like a fast spinning fan or a rotating wheel in a car. All right. Or a rotating planet. So these are the examples. So now angular momentum in case of rotation about a fixed axis. So angular momentum is a rotational equivalent of linear momentum. So let us consider firstly here some formulas that we already discussed in last lectures. So we know time rate of change of total angular momentum of system of particles about a point is equal to external torque on the system taken out the same point. So mathematically, the rate of change of angular momentum is equal to net external torque, where tau external is equal to 0 because the net external torque on the system is 0. So in that case, the angular momentum is constant. So we know uh, total angular momentum of n system of particles we can write like L is equal to summation I equal to 1 to n Ri cross Pi. Here Ri and Pi is the position vector and linear momentum of the ith particle respectively. So Pi is the linear momentum of ith particle. Now we know P is equal to mass into velocity. For Pi, their velocity will be what? Vi. So Pi is equal to mi vi. Linear momentum of ith particle is equal to mass of the ith particle into velocity of ith particle. All right. So let us consider a rigid body. rotating about a fixed axis. So here we have a rigid body and this is rotating about a fixed axis. For example, a ceiling fan rotating around its center rod. Yes or no? So similarly, in figure 6.17, we have a rigid body like this. So uh, in a circular path, here we consider a particle P rotating like this in a circular path. So at position and the position vector R from the origin O. So their linear momentum P is equal to mass into velocity, and the angular momentum of the particle is L is equal to R cross P. If we talk about the single particle, their angular momentum is R cross P at point P, where P is equal to mass into velocity is the linear momentum of the particle. So now here the important point is this. So the position vector, that is R vector, we can be written as R vector is equal to this one. R vector is equal to OP vector. OP vector is equal to OC vector. OC vector minus plus CP vector. Yes or no? OC plus CP is equal to OP vector. So this is the uh, representation of the position vector in terms of OC and CP. Now uh, we know R is equal to OC plus CP. This is the position vector. Now we know the angular moment of the particle is R cross P. Here R is OC vector plus CP vector cross P. So here P is the linear momentum. So we know the linear momentum, mass into velocity. So L become OC plus CP into mass into velocity. All right. Now solving this, so you will be get L is equal to OC vector cross MV plus CP vector cross MV. So this is simple mathematical terms. So we know magnitude of the linear velocity, that is V, and here V is the tangential at point P of the particle. So it will be V is equal to omega R perpendicular. This one. So here CP is the R perpendicular. CP is the R perpendicular. So V is equal to omega R perpendicular, and R perpendicular is CP. R perpendicular is the length of CP or perpendicular distance of P from axis of rotation, and Z is the axis of rotation. So we can write angular momentum L as L is equal to M into OC vector cross V plus M into CP vector cross V. So this is just simplification. So L is equal to mass into OC vector cross V plus M R perpendicular. R perpendicular, this one, perpendicular to CP. So it will be R perpendicular omega R perpendicular K cap around about a fixed axis. So CP, this one, CP cross V. Listen carefully. CP vector cross V vector is along the fixed axis, along the Z axis, and OC vector cross V vector is perpendicular to the fixed axis. Perpendicular to the fixed axis. This one. So L is equal to mass into OC vector cross V vector plus M R square perpendicular omega K cap. Now we know this one, uh, m r square perpendicular omega k is the angular momentum of the particle along fixed axis. So here fixed axis is z axis. So it will be L is equal to Lz plus this term as it is. So it will be O C cross MV. All right. Lz is the parallel to fixed axis. This one. Lz is parallel to fixed axis, or we can say Z axis, but L is not. Thus for a particle, angular momentum L is not along the axis of rotation. All right. Now, if we consider rigid body as a system of n particles, so total angular momentum of the whole rigid body is the sum of angular momentum of individual particles, and the total angular momentum of the whole rigid body we can write L is equal to summation I equal to 1 to n into Li. We know this RHS term. This shows the sum of angular momentum of individual particles. For first particle L1, for second particle L2, for third particle L3. So this is the sum of the angular momentum of individual particles. And this capital L is the angular momentum of whole rigid body. So there is a two term. First about L and about Lz. So it will be L is equal to summation I equal to 1 Liz plus summation I equal to 1 and OCI cross MIVI. So this is the angular momentum for a whole rigid body. Now Mi and Vi is the mass and velocity of the ith particle respectively. Ci is the center of the circle described by the particle, and Liz is the angular momentum of the ith particle along z axis. And summation I equal to 1 to n OCI into MIVI is the angular momentum of the ith particle perpendicular to z axis. All right. So this is the this term for perpendicular z axis. Angular momentum of the ith particle that is which is perpendicular to z axis. So components of L perpendicular to z axis is this one. L perpendicular is equal to summation I equal to 1 to n OCI cross MIVI. All right. So MIVI is the mass and velocity of the ith particle respectively. So Ci is the center of mass of the circle described by the particle. And components of L parallel to z axis is Lz is equal to this one. I equal to 1 and Li z. So Lz is equal to summation I equal to 1 to n mi ri square omega k. We know Lz is equal to m r square perpendicular omega k cap, where I is the perpendicular to distance of the ith particle from the axis of rotation. All right. So we know the moment of inertia of a body about the axis of rotation is I equal to summation I equal to 1 to n mi ri square. Therefore, component of L along the z axis is Lz is equal to I omega k cap, where omega is the angular velocity. So total angular momentum is this one. L is equal to Lz plus L perpendicular. So the important point here is this. we separated the angular momentum in two parts. First, the angular momentum along the L perpendicular. First, along the z-axis. Second one is the perpendicular to z-axis. Along the z-axis means parallel. All right, or perpendicular to that is represented by L perpendicular. So the total angular momentum is written as Lz plus L perpendicular. All right. Angular momentum in case of rotation about a fixed axis. So now rigid bodies whose axis of rotation is one of their symmetry axis are called symmetric bodies. So L perpendicular is 0 for symmetric bodies. Why? Because for such bodies, for every particle which has a velocity vi, there is another particle of velocity vi minus vi located diametrically opposite on the circle with center ci, and that is described by the particle. So such pairs will contribute 0 to L perpendicular. Therefore, symmetric bodies total angular momentum is L is equal to Lz is equal to I omega k cap, and this is important point. And we can say for symmetric bodies total angular momentum is I omega k cap. For bodies which are not symmetric about the axis of rotation, in that case L total angular momentum is not equal to Lz. Hence L does not lie along the axis of rotation. All right? Yes or no? So if we talk about the symmetric or non-symmetric bodies, so a body is called symmetric, rotationally symmetric about an axis. Condition is the mass is evenly distributed around the axis of rotation. So this means the shape is same in every direction around the axis. All opposite mass elements are equally placed. If we talk about an example, so solid or hollow sphere. Yes or no? Here, any axis through center. If we talk about the asymmetric bodies, or we can say unsymmetric, so a body is asymmetric if its mass is not evenly distributed around the axis of rotation, or we can say the shape is irregular. Mass may be concentrated more on one side. If we talk about the example of asymmetric bodies, an L-shaped object. All right. Now, relationship between components of angular momentum and torque. So we know rate of change of total angular momentum, that is dl upon dt is equal to tau. For a rotation about fixed axis, only those components of external torque are considered which are along the axis of rotation. So therefore the torque tau is taken along the axis of rotation, that is tau equal to tau k cap. Tau is the magnitude and k cap is the direction. So we know the total angular momentum, that is L is equal to Lz plus L perpendicular. Here direction of Lz is fixed along k cap. It follows that for rotation about a fixed axis is dlz upon dt is equal to tau k cap, and dl perpendicular dt is equal to 0. So the rotation about a fixed axis, the component of angular momentum perpendicular to the fixed axis is constant. dl perpendicular dt is equal to 0. Now, uh, Lz is equal to I omega k cap. So we can write d Lz upon d Lz dt is equal to tau k cap. So just put the value of Lz. We know that is I omega k cap. So just put here. You will be get I d I omega dt k cap is equal to tau k cap. So here the differentiation k it will be d I omega upon dt is equal to tau. Now, if the moment of inertia I does not change with time, in that case tau equal to I d omega upon dt. So tau equal to I alpha. Here alpha is d omega upon dt, or we can say angular acceleration of the body. Angular acceleration of the body. So all the formulas that we discuss here are very important. Now we know d I omega upon dt is equal to tau. So if external torque is 0, the net external torque on the body is 0, in that case d I omega dt is equal to 0. So Lz is equal to I omega, so that is constant. So we can say Lz equal to constant. All right. Conservation of angular momentum for rotation about a fixed axis. All right. For a symmetric bodies, Lz is equal to L, magnitude of the total angular momentum. This is for the symmetric body. And mathematically we can write L is equal to I omega is constant. So when moment of inertia of body changes from I1 to I2 and angular velocity changes from omega 1 to omega 2, product of moment of inertia I and angular velocity omega remains same, and that is I1 omega 1 is equal to I2 omega 2. This equation is valid when external torque on rotating body is 0. In simple words, we can say if the system is isolated, if the system is isolated, no push or twist from outside, then whatever angular momentum is it had in the beginning, it will continue in such a way that L equal to I omega remains the same. So we know I here I1 omega 1 is equal to I2 omega 2. So if one increases, the other decreases like a balance. All right. Examples of conservation of angular momentum. So a girl rotating on a swivel chair, her arms outstretched. So imagine this carefully. So a girl is sitting on a freely rotating chair, holding small. Uh, Here, girl is only rotating on a freely chair, and she spins slowly while her arms are stretched outward. Look at here, figure 6.32. The arms of the girl are stretched outward. Now, what happens? Think about it. What happens? So when she pulls her arms inward, when she pulls her arm inwards, think about it. So in that case, her moment of inertia decreases because the mass is now closer to the axis. All right. When her arm is closer to axis, the moment of inertia decreases. All right. So to keep angular momentum constant, her angular velocity increases. It means omega I1 omega 1 is equal to I2 omega 2. Yes or no? So omega 2 increases. So bringing the arms closer to the body has the opposite effect. All right. So second example, let's talk about a acrobat. So an acrobat uses the principles of conservation of angular momentum when performing spins or flips. All right. So the acrobat jumps, when the acrobat jumps into the air, into the air and curls up, what happens? Think about it. So their body becomes compact. So we can say moment of inertia decreases. All right. So they spins faster in the air just before landing and stretch their body. So moment of inertia increases. All right. So they slow down the spin for a smooth and safe landing. Here we assuming no external torques. All right. No summary. The rate of change of total angular momentum equals external torque. So dl upon dt is equal to tau external. Angular momentum of a system is sum of angular momentum of all particles, or we can say individual sum of angular momentum of all particles. This L is equal to summation I equal to 1 to n Ri cross Pi. All right. Total angular momentum has two components, parallel and perpendicular components to rotation axis. That is L is equal to Lz, that is parallel, plus L perpendicular, that is perpendicular. All right. Angular momentum along axis is related to moment of inertia, and angular momentum velocity is Lz is equal to I omega k cap. For symmetric bodies, total angular momentum lies along the axis of rotation. So L is equal to Lz I omega k cap. And when moment of inertia of body changes from I1 to I2 and angular velocity changes omega 1 and omega 2, product I omega remains same. Mathematically it will be I1 omega 1 is equal to I2 omega 2. All right. Now we have a practice questions, and this is homework for you. First, if a rigid body is rotating about a fixed axis with angular velocity omega, what is the expression for angular momentum along the axis of rotation? So in this question, you have to find out the angular momentum along the axis of rotation. All right. Second question, for a particle at position r with linear momentum p, what is the expression for its angular momentum? So here you have to find out the expression for its angular momentum. Next one, if angular momentum L equal to 10 kg meter square per second and angular velocity omega is equal to 2 radian per second, what is the moment of inertia of the body? So here you have to find out the moment of inertia. Fourth one, a disk with moment of inertia 4 kg meter square rotates at 6 radian per second. If its moment of inertia changes to 2 kg meter square, what will be its new angular velocity? So here you have to find out the new angular velocity. Fifth one, if a particle of mass 2 kg moves with velocity 3 meter per second at a perpendicular distance of 4 meter from an axis, what is its angular momentum about that axis? So in this question again you have to find out the angular momentum about an axis. All right. So this is practice questions and this is homework for you everyone. Thank you for your attention.